Hello there. Are you ready for all kinds of reactions? Anyway, it might be helpful to look at your model with an alkyne built, triple bond between the two carbons, and notice that you can't rotate the carbons fixed in that triple bond. Groups around it, yeah, it's almost like a straight rod. It's very linear, rigid, and in fact, it's used in applications to exploit that rigidity. So that's a structure-function sort of relationship. As a reminder, we're going to be drawing them a lot. So make sure you're following the linear. So this model that I've built has 1, 2, 3, 4, 5, 6 carbons. So far I've only drawn 4 carbons. So it's this 2 ethyls on each end. It's an internal alkyne. So 1, 2, 3, 4, 5, 6. I could have also rotated, so I drew it kind of like this, but I could have drawn it up like that. So I'm allowed to rotate those single bonds still, of course, but the bonds with the alkyne stay fixed. 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Same thing, right? So this would be 3, because that's where the alkyne starts, hexyne. Okay, we will be naming them. So 3-hexyne or hex-3-ine would be another way to name it, to indicate where the hexane is the parent chain, ine gets the suffix for alkyne, and 3 is where the alkyne starts. Now, it's very appropriate to learn about alkynes of reactions after, okay, I'll stop, the learning about alkenes, because it's just another pi bond. So they're very similar. We're going to learn the same sets of reagents, and in some cases that just means doing the reaction twice for 2 pi bonds. In other cases, something surprising happens. So we will, of course, spend a little more time on that, but they both contain a pi bond. So it's really nice to learn those side by side. So we're going to jump into it, kind of refreshing our memory on what happens with the alkenes with those reagents, and then try to imagine what happens when we add one more step. And that will shorten our mechanisms a little bit, because we're going to take it for granted that we know the alkene mechanism up to a certain point, and then carry on that with the understanding that we have extra reagent. So we'll jump right in with HX. So HCl, HBr, HI, so hydrohalogenation. So adding a hydrogen to one carbon, halogen to the other. Which carbon gets which? That follows Markovnikov's rule. In other words, the halogen went to the more substituted, the new group, the nucleophile, Markovnikov. And because it involved a carbocation intermediate, and it was not selective for any particular stereoisomer. So enantiomers, if they could form, they would form, right? So what we're going to do is repeat sort of that idea, only with 2 pi bonds instead of 1. So same concept though. The electron-rich pi bond grabs that H. It's attracted to it owing to this polar bond being delta plus, delta minus, right? Which makes that bond easy to ionize, to give the electrons to bromine to make a bromide. We're starting with a deuterium here, just so that when we add an H, we can tell which one is the new H and which one was there all along. So we're using the heavy isotope of H just so we could track these a little bit easier without having to color code it necessarily. So let's put the D and the H on the same carbon because we're following Markovnikov's rule. We lost a pi bond. Let's put the carbocation on the more substituted carbon, thanks to Markovnikov. But notice it's a funny looking carbocation. It's actually sp, it's linear because it's got a pi bond, right? So still only 2 groups. It's got a pi bond, 1 sigma bond, and then no third group. So it's actually sp hybridized linear. Let's write that down. Okay, now because it's linear, it's flat, the bromide, the nucleophile, it's going to, of course, attack that carbocations, and that's not going to live long. And it could do so from the top or from the bottom. So if it goes through the top route, and we have our H and our D stay the same, that just means our bromide is up here and our methyl's down here, versus keep the H and the D the same, those didn't change. The bromide's on the bottom, the methyl's on the top. So if you control the stoichiometry, so you have one equivalent added only, you can have an alkene that has been halogenated. So let's write that out. The result, one equivalent of HX stops at mono halogenated alkene. So we can isolate that if that's what we prefer to do, or it can keep going, because what do we know about alkenes? They react with HX. So if we have, let's try HI, so it's not so neglected, and we add two equivalents, that means both pi bonds can react. We don't have to stop after one equivalent. So one equivalent means a ratio of 1 to 1 for that. If we have two equivalents, that means a ratio of 2 to 1. And since there's two pi bonds here, that means it would take two of these to fully react both pi bonds. So let's show that consequence. What we will do is save ourselves a little work. We've proven that mechanism already from the top, that one equivalent gets us straight to, so that we're not drawing it again, the scenario with H. And notice this is not deuterium anymore. This example has only H in it. The monohalogenated alkene. There are not two different alkenes to draw, simply because these two groups are the same. So it wouldn't have made a difference whether I put it on the top or the bottom. I could color code it, or I could have deuterated it, so showing that, you know, one of the H's is new, right? But we also have that I minus floating around. So that attacked and came here for that carbocation. Now that's the end of step one. That was one equivalent. Let's add the second equivalent and see what happens. Second equivalent of HI. Let's draw the bond. That pi bond attacks, leaving group leaves. Follows Markovnikov's rule. Another H comes in. Oops, I actually drew an alkene. Pi bond's gone, right? But following Markovnikov's rule, all the H's go on the carbon with H's. So if I already had one blue H, I'm going to have a second blue H, right? This is the carbon that had methyl and an I, and now it is a carbocation. So this is the same mechanism from the alkene chapter, only there's a halogen as part of the substrate now. So now the I minus says I see a carbocation. This, by the way, is an sp2 hybridized carbocation, not sp, because we have three groups to it, no pi bond. Just like the old kind we've seen many times. Attack. Lo and behold, we get two halogens on the same carbon. Clean this up. You should be able to recognize that I'm drawing the same thing. Two methyls. One carbon, one carbon. Two halogens, two halogens. So how would we describe this particular product? We could say from an alkyne, if we had two equivalents of HX, we can arrive at a geminal. That means sharing the carbon, geminal dihalide, derived from the root. Twins, Gemini, they share the same parent carbon. So the two, if they're on the same carbon, they are geminal. So geminal dihalide. Of course, we did add new H's. I didn't draw them in because as I simplify the structure for the final product, they don't have to be, but if it makes you feel better, you could draw on the new H's. There's two blue H's there. The original black H is still there. And then this CH3 has all original H's. Okay, so adding twice, we would get a haloalkane the first time if we use an alkene, but if we started with an alkyne, we get a geminal dihalide. Let's do another halogenation reaction, this time with, instead of HX, let's do X2. Remember we did that with chlorine and bromine with the alkenes? So with the alkenes, the regiochemistry was irrelevant, right? Because it was a matter of which carbon got which group, and because it's a dihalide that we're adding, each carbon will get a halogen. So irrelevant. So we don't have to concern ourselves with that too much, but we did have to note that it was anti-addition. So let's evaluate the same idea with 2 pi bonds, and we'll do that step by step. Loss of the first pi bond and loss of the second. The mechanisms are the same though. So we draw our chlorine with its induced dipole as it approaches the electron-rich region of that alkyne, excuse me. Let's draw some lone pairs so it can attack. Back down, and then this leaving group can leave. We get that chloronium ion type intermediate, only it's even more strained because there is a pi bond as part of this 3-membered ring. I mean, that talk about strained, it was already strained as it was, but now it's particularly strained. Short-lived, right? So, but we'll likewise still have a backside attack. Anti. Because it's that backside attack results in anti. What does that mean when we still have a pi bond left? So notice the chlorine, this guy that was the first chlorine on, winds up here. We still have a methyl. The methyl is above the new chlorine, so it gets pushed up to the top to make space for that new chlorine. So anti corresponds to trans, right? Transchlorines. So trans dihalogenated alkene with only one equivalent, right? Okay, so like the previous step, we're going to say thank you for doing that mechanism. We're going to take advantage of that because now we're going to show what happens with 2 equivalents. So after 1 equivalent, I'm just going to draw instead of drawing the whole mechanism that we did above, we're going to do this with bromine now. I'm going to go straight to the answer. I know I get a trans dibromide, and whatever R groups were there are now trans as well. So methyl, methyl. Okay, now let's get ready for the second equivalent. And we're starting with an alkene. We know how to do this. So I could just say, look at the previous chapter, but it doesn't hurt to revisit these mechanisms. So Br delta plus, Br delta minus. Okay, so we do our bromonium ion intermediate. I'm showing the bottom attack right here, right? We'll look and see if that really matters, that we have to draw it all out or not, because we can acknowledge that all paths are possible, but bottom versus top attack, but sometimes they are less relevant and to belabor. So let's see if that's important. Remember that, side note, for an alkene, if I need to start including stereochemistry, which I do because I lost the pi bond, go into a tetrahedral carbon, so that means that this I'm going to represent the bottom. I'm going to let the bottom groups be wedges. So I'm going to turn it up this way. Bring that alkene up toward me. And let the top groups be dashes. Okay? So I brought it up toward me. I'm looking at it. That means that when I get to this point where I have to draw in dashes and wedges because I need to illustrate that anti-relationship, it makes sense. See how those bromines that we added that were trans before stay trans right there. Okay, so however you chose to do the addition of the bromonium, or to form the bromonium ion intermediate, you have to attack from the opposite face. Which carbon doesn't matter because it won't change the outcome. We're going to have a bromine on a new bromine again. On each carbon, resulting in 2 net bromines on each carbon 4 bromines total. Okay, so what that means is it really does have an anti-relationship, and we could have had all these other ways of drawing it. So if I draw it, like, it would look like this for the specific route that I drew. So those planar bromines are the newest ones added, and the out-of-plane ones are the ones that are resulting from the previous step. But notice that I don't have a stereocenter because there's no chance of getting one. I have destroyed that by adding 2 of the same group to each carbon. So I will not have a stereocenter here when I start with an alkyne, and I will not have a stereocenter here when I start with an alkyne. Therefore, in some ways, this is actually easier. You don't have to think about that, and you just say, well, this equals this tetrahalo alkane. See that? No enantiomer to draw. It's not chiral. What else can we say about it? Well, it's nice to have the words to describe the product because we will be talking about them when we think it's synthesis, right? Tetrahalogenated alkane. Now that's actually a useful thing to make. Something with 4 leaving groups, right? You can imagine that in a synthesis being useful. Okay. What else could we do that is somewhat familiar? We can reduce alkynes, just like we can reduce alkenes. So H2 palladium on carbon, catalytic hydrogenation. Catalytic hydrogenation. So sometimes it's platinum or some other catalyst that's a transition metal, but palladium on carbon is a popular one, the H2 gas. Usually the stoichiometry is a little hard to control, so it doesn't always note this, but you're going to have to assume it's essentially excess. So what we get is complete reduction. You can't really control one equivalent very easily. Part of the nature has to do with the fact that it's a gas, and that some of the original alkene just keeps reacting, or the alkyne, when it becomes an alkene, you don't get to stop it there because alkenes react to become alkanes and you get a mixture. So it doesn't help to play with stoichiometry to stop this from doing that. So it's fully reduced. And one thing we know about alkanes is they're more or less a dead end synthetically. So we don't often want to do that. It loses functional group. So if we're doing a synthesis and we're at the very end and we need something to become an alkyl chain, fine. But a lot of the times we want to maybe only remove 1 pi bond. And luckily there's a way to do that.